Ever wondered why two perfectly competent engineers can design wildly different architectures for the same problem? It's because every big decision hides a trade-off. In the next few minutes, we'll walk through the 10 most common design dilemmas you must weigh before building a scalable system. Picture the fan-shaped diagram now on screen. We'll move from left to right across each blade. 1. Vertical versus horizontal scaling. First, the foundation, scaling strategy. Vertical scaling beefs up a single box, more CPU, more RAM, but a hard ceiling. Horizontal scaling spreads the load across many machines, unlocking near infinite growth at the cost of orchestration complexity. When capacity spikes unpredictably, horizontal usually wins. 2. SQL versus NoSQL. Next, the data store choice. SQL offers rigid schemas, ACID guarantees, and mature tooling. NoSQL sacrifices some structure to excel at flexible distributed workloads. If you need relational joins and strong consistency, stick with a SQL. If you're chasing petabytes in rapid iteration, NoSQL might fit better. 3. Batch versus stream processing. Third, data movement. Batch pipelines collect records and process them in chunks. Great for nightly reports. Stream processing handles events the moment they arrive. Perfect for fraud detection or live metrics. Remember, lower latency demands higher operational rigor. 4. Normalization versus denormalization. Fourth, schema design. Normalized tables reduce redundancy and protect data integrity, but require expensive joins. Denormalized tables duplicate fields to accelerate reads, trading storage space, and update complexity for speed. Transaction-heavy systems lean normalized, read-heavy dashboards lean denormalized. 5. Consistency versus availability, CAP perspective. Fifth, the infamous CAP triangle. In a network partition, you may guarantee consistency, all nodes see the same data, or availability, every request gets a response, but not both. Mission-critical banking apps favor consistency. Globally distributed social feeds often prize availability. 6. Strong versus eventual consistency. Sixth, zoom in on consistency itself. Strong consistency ensures every read reflects the latest write, no surprises, higher latency. Eventual consistency lets replicas lag briefly, achieving stellar throughput and geo-replication. Choose strong for ledgers, eventual for user timelines. REST versus GraphQL. Seventh blade API style. REST exposes fixed resources, simple, cache-friendly, but often overfetches. GraphQL lets clients ask for exactly what they need in one round trip. However, it adds server complexity and tricky caching. Mobile apps with chatty networks love GraphQL. Public APIs often stay with REST. 8. Stateful versus stateless services. 8th, request handling. Stateful services keep client context on the server, easy session logic, but sticky load balancing. Stateless services treat every request as new, enabling elastic scaling and fault tolerance. Modern cloud natives push hard towards stateless designs. Hasher 9, synchronous asynchronous processing. 9th, interaction style. Synchronous calls block until a response arrives, simple but brittle under spikes. Asynchronous workflows hand tasks to queues, free the caller, and reconcile later, boosting throughput at the cost of complexity and eventual consistency concerns. 10. Read-through versus write-through cache. Finally, caching strategy. A read-through cache fills on a miss by pulling from the database, easy to drop stale keys. A write-through cache updates the cache and backing store together, guaranteeing freshness but adding write latency. High read, low write workloads prefer read-through. Real-time leaderboards may need write-through. Closing. Those are the 10 levers every architect must pull. Each solves one pain while sharpening another. Keep this fan of trade-offs handy, and you'll design systems that scale gracefully, adapt quickly, and most important, serve your users reliably.